Hey everyone! In this short video, we're going to be looking at training language models to follow instructions with human feedback. A big problem with language models is that they're misaligned with human wants. They make up facts, which means hallucinating or confabulating, they generate biased or toxic text, and they fail to follow instructions or constraints provided in prompts. You might not be aware of how significant these problems were because popular models like ChatGPT have made significant advancements in this field due to the research that I'm going to talk about. This misalignment stems from the fact that the training objective, next token prediction, is not the same as the user objective, following the user's instructions helpfully and safely. Unfortunately, we cannot change the training objective because of the sheer scale of training data required for language models. OpenAI's scaling laws show that large language models consistently improve in performance as the model size, training data, and compute increase. This is why cherry-picking examples off of the internet that align with our values simply isn't an option. Instead, we must rely on more data-efficient methods, such as supervised fine-tuning and reinforcement learning, to make up for this lost performance. InstructGPT, the model that emerged from this research, was trained in 3 steps. In step 1, the objective is to fine-tune an underlying LLM, GPT-3 to be exact. This creates a supervised fine-tuned model, or SFT for short. This is done using data produced by 40 workers hired on platforms such as Upwork and Scale AI. The dataset included 13,000 prompts with ideal responses written by each of those labelers. These responses were closely aligned with OpenAI's values: helpfulness, safety, instruction following, and truthfulness. Moving on to step 2, the objective is to train a model that ranks various responses, the reward model, or RM for short. This is used later on in step 3 for reinforcement learning. The underlying model is the 6 billion parameter supervised fine-tuned model from step 1, with the head replaced. The dataset here also contains human-labeled content, A/B rankings of between 4 to 9 responses on 33,000 prompts. This leaves between, roughly, 200,000 and 1.2 million samples. This model is also trained using supervised fine-tuning. Finally, in step 3, the objective is to use reinforcement learning to train a policy that aligns with OpenAI's values. The reinforcement learning algorithm used is PPO, which stands for Proximal Policy Optimization. This is a data-efficient, on-policy training method developed by OpenAI. The reward model is what makes this task supervised despite there being no human annotator. The underlying model that is being trained is the supervised fine-tuned model from step 1 with various parameter counts. The dataset is comprised of 33,000 prompts that were made by users in the OpenAI playground. Here goes the training loop. First, a prompt is sampled. Then, the on-policy supervised fine-tuned model generates a response for that prompt. The reward model rates that response, and this is used as a loss to update the weights using PPO. In this final step, OpenAI trained 2 different models, PPO and PPO-PTX. I'll quickly explain the difference between these two. They found that, after using the PPO model that was trained using reinforcement learning, the performance of downstream NLP tasks had degraded. The intuition was that the reinforcement learning had forced the output distribution to drift too far from the original pre-training phase, and therefore, they introduced a new variant, the PPO-PTX model. In PPO-PTX, they add a penalty factor, a callback-Libler divergence between the probability distribution of the next token in the PPO-PTX model that is currently being trained, and the original SFT model's probability distribution. What this does is it changes to loss when the model trained using reinforcement learning starts to drift away from the original output distribution, thereby limiting the effect that training with instruction following has on the policy. Moving on to the results, OpenAI qualitatively evaluate the performance of 5 different training configurations against the 175 billion parameter supervised fine-tuned model. They do this by asking human labelers to rank the responses of each model, similar to the data that was used in step 2. In other words, the 175B SFT model is the baseline, and the GPT with prompting, SFT, PPO, and PPO-PTX models at different parameter counts are each tested against the 175 billion parameter model. The parameter counts they test are 1.3 billion, 6 billion, and also 175 billion. As you can see, the win rate of the 175 billion parameter SFT model against itself is 50%, which makes sense, they're the same model. However, if you look at either of the PPO models, Even with 1.3 billion parameters, which is over 100 times less, human annotators still preferred the responses to the much larger model. This performance increase holds as the parameter count increases, surpassing over a 60% win rate. It should be noted that achieving this performance with far fewer parameters results in significant cost savings. Beyond this, NLP tests found that PPO models resulted in improved truthfulness, reduced hallucination, and reduced toxicity. This method did not have a large impact on the inherent biases that these models have, however. The PPO-PTX model mitigated the alignment tax, which is a phenomenon where the performance of downstream NLP tasks degrade. Furthermore, the PPO models both showed generalization to following instructions in languages outside of the training distribution. This work has clearly been instrumental in advancing large language models to their current state, as ChatGPT, as well as many other LLMs, use this method in their training now. Future work that has been done in this domain includes enabling humans to edit responses and using this in the training phase, verifying the correctness of each token as it is being generated, and also using sparse autoencoders for alignment. This paper states that more open questions include trying more methods to reduce harmful or dishonest text, as the model still makes simple mistakes, combining this method with control codes for steerability, and also testing different training algorithms to the ones presented here. Thank you for watching.